Whoa. So we have a huge list of authors, many of which used to work for a bigger company, but they're now working somewhere else. They're working for Algorand. So it's the first time I've ever introduced someone from Algorand. So I'm going to pass it over to Shai, who's sharing the wrong screen. You're sharing the presenter view.
Yeah, I'm not exactly sure how to fix that, but we'll see in a minute.
I think when you do share screen, you can select which window you want to share.
Yeah, but then it switches to the other window. So I need to first start the presentation and then mess with Zoom, which is not clear how to do that.
Maybe put it on presenter mode and then do the Zoom sharing.
Yeah, that's what I'm trying to do. But when it's in presenter mode, then it gives me so much fewer options on the Zoom thing. Oh, I have an idea. Let me try to get rid of the big screen and work only with the little screen, and maybe then it would let me do stuff.
Yay, that works.
Good, thank you.
Right, okay, so over to Shai, and the question is, can a blockchain keep a secret? Shai.
So as Nigel said, this is joint work with Fabrice, Greg, Sergey, Hugo, Chengyu, Tal, and Leo. And the question that we really want to ask, oh, come on. Did you hear that? That wasn't planned at all. Turns out that if you don't explicitly clear everything ahead of time, then it shows the... Okay, let's try again. The thing we really care about is, can a blockchain be a trusted third party? And by a blockchain, I mean a public proof of stake blockchain. And by a trusted party, I mean what we always mean in cryptography. This is a party that has clients. The clients give it inputs. They ask it to compute something. Some of these inputs might be secret, but they are, the trusted party would still compute whatever it was asked and give everybody their output and forget about everything else and never reveal anything else about the secret inputs. So this is what we want. And we would like a blockchain to play the role of this trusted party, and can it? And the answer is not really. I mean, blockchains these days are great for things like integrity and immutability properties, but the secrecy story is a lot harder to tell. So in this work, we care about secrecy, and we care about a very basic setting. There is a client of the blockchain, one of these dogs in the previous slides. They have a secret. They want to give it to the blockchain and tell the blockchain what to do with that secret, like reveal it only when the time is right, or more generally, use it only in some prescribed manner that I'm telling you. Here's an example. I publish a puzzle. I give the blockchain the solution to this puzzle, and I tell the blockchain, please reveal the solution if nobody solves the puzzle by next week. So this is a very basic setting, but it can form the basis for many applications. You can do this thing, you can do many other interesting stuff. What we want to achieve, well, there is a security and there is an efficiency consideration. The security is very simple. The secret should remain a secret, that's it. The adversary shouldn't learn what it is, but the blockchain should still be able to recover it when the time is right. Now, this is our solution needs an honest majority, and since we're talking about proof of stake blockchains, then it's an honest majority of the stake. But for this presentation, just imagine honest majority of the participants. Importantly, we considered a mobile adversary. So the adversary can corrupt a minority of the stake this week and a different minority of the stake next week. And even so, we want to make sure that the secret remains a secret. In terms of efficiency, what we're looking for is a scalable solution. And very specifically by scalable, I mean a solution where the communication and the work doesn't increase as time goes by, as the blockchain has more history, or as there are more nodes or more stake. The solution, the complexity of the solution should be some fixed polynomial and a security parameter, and that's it, depending maybe polylogarithmic on everything else. The other efficiency consideration that I call plausible scalability essentially means that we don't want to use obfuscation or things like obfuscation. We want something that can potentially be implemented someday. And in particular, the approach that we use in this work is to rely on proactive secret sharing. So what is a proactive secret sharing? Proactive secret sharing is a long-running system where some secret is shared among a committee. The committee can be everybody, or there can be different committees at different times. But every so often, there is a periodic share refresh protocol where the committee either passes the secret to another committee or just refreshes the secret among itself. And the property is that the secret remains secret as long as each committee separately has honest majority, even if different parties are corrupted at different times. So this is a technique that's been used for 20, 30 years now, and we want to use this type of approach in our solution as well. But there is a problem. In our solution, it's very far from being trivial because I want a solution to be scalable, which means that I can't have everybody participating in the protocol. I need to have a small committee that participates in the protocol so that the solution doesn't get more complex with more people. But if there's only a small committee and if there's a mobile adversary, then, well, the mobile adversary just can corrupt the entire committee and then it learns the secret and it's all over. So what do we do? This is not the first time that question has been asked, and there is previous work in the setting of a blockchain with committees, but previous work just assume that the committees remain mostly honest. Whereas in our work, we actually design a mechanism to ensure that property. So that's the major difference. And the type of solution that we are using is to keep the committee anonymous. So the adversary cannot target them for corruption. And there's a technique called player replaceability. It's been used in systems like Algorand, where a committee is a one-time thing. If I'm a committee member, all I need to do is send one message and then I'm off the committee. And once I'm off the committee, I don't have any secrets that I know. So once the adversary know who I am, there is no point in corrupting me anymore because I don't know any more secrets. This is what we want to do. And there's a question of, okay, how do we do that? How do we reshare a secret among committee if we don't know who the committee is? Here are some things that don't work. One way to choose a committee in an anonymous way is for the committee to select itself. So I'm selecting myself to the committee and the adversary doesn't know that I'm on the committee until I say something via some mechanism called sortition that I'll mention in a slide or two. But this type of thing can't work here. I mean, if I select myself and I don't say anything, how can anybody give me shares of a secret? The previous committee doesn't know who I am. So we don't know how to make that work. Well, maybe in that case, the previous committee can just select the next one. If I'm on the current committee, I'm just going to select my successor in the next committee. Okay, that doesn't work either, because if I'm a bad guy, I will choose a bad guy to the next committee. And if I'm honest, well, then I can choose at random, but still I'm going to hit a bad guy with some probability F. So the committee will have more and more dishonest people as time goes by. And I want to point out that even if I force bad guys to behave honestly by asking them to prove stuff, that doesn't work either, because, okay, so I choose my successor honestly, but I'm a corrupted person, and now I know who my successor is. I can just go ahead and corrupt them after the fact. The adversary is mobile. It can corrupt different people at different times. So that doesn't work either. So what do we do? So the things we observed is that it would really be nice if we can implement the following functionality that I call a target anonymous channel. A target anonymous channel have M visible input ports and M hidden output ports, and some random assignment of the output ports to a subset of the players. So anyone can send a message on the ith input port, and this would be routed to one of the participants, but even the sender doesn't know who the message will arrive to. If we had this type of functionality, then the current committee can just reshare their secret on these M input ports, and these secret will arrive at the next committee. Are just the people that are sitting at the output ports, but nobody knows who they are. I want to point out that this doesn't solve everything. Even if you had that, there's still some work to do, but that's sort of the major problem here. If you could implement that, then other things you can do easier. So how do we do that? We're going to use the three following tools. We're going to use cryptographic sortitions. I mentioned that before. It's based on verifiable random function, and it's a way for me to select myself to the committee and later on prove to everybody that I was indeed entitled to sit on that committee. So I can toss this coin that with probability P says yes, you're on a committee, and I can prove to everybody that I tossed the coin correctly. So that's one tool. The other things that we need is a PKI and a broadcast channel. And for those, we're just going to use the blockchain. And the third component that we use is an anonymous public key encryption. What that means is a regular public key encryption with semantic security. But in addition, it has this property that if I have two public keys and a ciphertext encrypted under one of them, it's hard to tell whether I encrypted it under the first public key or the second one. So it provides a way for anonymous communication. And with that, I can try to implement some approximation of this target anonymous channels. So I'm going to start with an M members nominating committee that self-selects itself using this sortition mechanism that I said before. So they select themselves, but they don't have any secrets. They don't need to know any secrets. Their job is just to nominate the committee that will know secrets. And then each nominator will choose a nominee among the N parties. And if that nominator is honest, then it will choose the nominee honestly. And if that nominator is dishonest, then it can do whatever it wants. Then what it's going to do is it's going to draw a new pair of public and secret key for some public key encryption scheme. It's going to encrypt the secret key under the long-term public key of the nominee to get some ciphertext. And that encryption is the one where we use the anonymous public key encryption. So the ciphertext doesn't betray the public key or the party that it was encrypted under. And then it's going to broadcast the new ephemeral public key and the ciphertext that encrypts the corresponding secret. What that does is now everybody see this new public key PKI prime and can send messages, can send encrypted messages, broadcast the encrypted messages under this public key. But nobody knows who can see the corresponding messages because the ciphertext encrypting the secret key is anonymous. On the other hand, P sub j, the nominee, can recover the corresponding secret key and then decrypt all these messages. So in a sense, we established an anonymous channel where the target is not known, but everybody can send on that channel. And if the nominator was honest, then the adversary doesn't know who the channel leads to. One important property of this implementation is that we do not ask the nominator to prove anything. So that means that corrupted nominators can, for example, nominate their friends or themselves, or just send, publish a completely invalid ciphertext or public keys. And the reason we don't ask them to prove anything, well, the main reason is that proofs just don't work. I already said that before. Even if I force to behave honestly and I'm corrupted, what I can do is behave honestly, figure out who I nominated, and then corrupted that person. So it's not going to help me trying to prove stuff. And also, these proofs are expensive. The statements that I'm going to have to prove are long, in the sense that I'm going to have to prove that there exists some one of these N public keys that's the end, who's the end of that anonymous channel. So this is a statement with long, this is a long statement. So the solution is not scalable. You can still make the proof short, but the work to produce this proof necessarily is long. So let's talk about the resilience of this implementation. The fact that the nominators don't need to prove anything means that the adversary here has a double deeping strategy. The adversary controls some F fraction of the stake or the parties. So because the nominating committee self-selects, it would control roughly an F fraction of the nominators. So corrupted nominators will choose corrupted nominees, but honest nominators, well, they have a probability of a half of choosing a corrupted nominee if they choose at random. So the overall committee will have roughly 2F fraction of corruptions. That means that if we want to ensure honest majority with this implementation of the chosen committee, then we need to assume that the adversary controls strictly less than 1/4 of the stake of the blockchain. So the way the overall solution looks like, we have these nominating committees that select themselves. Each nominating committee then generate these target anonymous channels that lead to the secret sharing committee. And then the previous secret sharing committee will use these target anonymous channels to send their secret forward to the new committee. The resharing by the secret sharing committees require proofs. So if I'm on the secret sharing committee and I send forward some version of my secret, I need to prove that I did it correctly and that the thing that I sent are indeed resharing of my shares. But these proofs are only for short statement with short witnesses. So both the statements and the witnesses are of size that depends only on the size of the committee rather than the entire population. Therefore, this solution is scalable. So the end result is a scalable proactive secret sharing protocol with display replaceability property that I talked about, where as every member talks only once and then it's off the committee. It's secure, assuming that the adversary controls strictly less than 1/4 of the stake, so there's room for improvement here. It can be implemented under all these public key assumptions that we like, except that we actually need to make some conjecture, and I will spend a few slides in a minute talking about that conjecture about anonymous encryption under selective opening attacks. And there's an open problem here. And that solution can conceivably be made practical. I mean, we didn't implement it. We didn't even try to estimate how complex it would be, but definitely sort of a fixed thing in the security parameter uses only sort of the known techniques of proving stuff about encrypted inputs, and we believe that you can make it practical. So let me switch gears and talk a little bit about the open problem that's the conjecture that we need to make in order to prove security. So our solution broadcasts encryption under anonymous public key encryption, which means that the adversary can see the public keys and can see the ciphertext, and then decides which public keys it wants to corrupt to see the corresponding secret keys. So that brings up the question, so we know that the adversary only corrupts an F fraction of the keys, but can it nonetheless manage to read much more than an F fraction of the encrypted ciphertext? So we have our M ciphertext. They're encrypted under M out of the N public keys. And the mapping of which public keys encrypt what ciphertext is computationally hidden. But does that mean that the adversary cannot corrupt many more of the keys that were actually used for encryption? Right now, I marked these keys in blue. Is the fact that the adversary corrupt only F fraction of the entire population means that it can only corrupt more or less up to F fraction of the blue keys? That's a question. And it's a question about adaptive opening of keys. So an adaptive adversary sees the keys, sees the file ciphertext, then decides to open the keys one at a time. I want to see this, the secret key of this public key. Now I get it. Now I want to open the next public key, et cetera, et cetera. Another type of adversary that's interesting to talk about is a semi-adaptive. It still sees the keys in the ciphertext, but then makes one-shot decision about which subset of the keys it wants to open, and then gets these secret keys, and there is no more adaptivity after that. If it was secrecy, for the case of secrecy, it's very well known that semantic security does not imply secrecy under selective opening, even if the adversary is semi-adaptive. So we have negative examples of crypto systems that are semantically secure, but nonetheless completely broken under selective opening, even for a semi-adaptive adversary. For anonymity, it turns out that that's not the case. Indeed, we prove a lemma that says that if the public key encryption is anonymous, then a semi-adaptive adversary open at most F fraction of the keys cannot open much more than F fraction of the blue keys, except with negligible probability. The thing to take home from that is that anonymity behaves very different than secrecy when it comes to selective opening. And we conjecture that the same holds for fully adaptive adversary. We could not prove that. We actually have a reduction that I believe works, but we couldn't figure out how to analyze it. Just a complicated combinatorial game that we couldn't find a handle to analyze. Nonetheless, I believe that that conjecture is true, and this is an interesting thing to try to prove. So with that, I'm way ahead of time, but I'm done with the things that I wanted to say. So let me just state some open problems and future work directions. One of them is to prove the conjecture that I just stated, that anonymous public key encryption is still anonymous even under selective open attacks. Another direction of future work is to do more with the secret. Don't just keep the secret, actually compute on it. This was our original motivation. We wanted the blockchain to be a trusted third party, which means that it gets many secrets and it computes on them. We actually have some follow-up work that does that. The techniques that we use for sharing the secrets are essentially the same techniques that you can use to compute on it. The difference is not that large. Yet another direction is to improve the resilience of the target anonymous channels. Right now, the implementation that we have, if you want the end result committees to have honest majority, then you need to assume that the adversary control at most a quarter of the stake. And hopefully you can improve it to anything less than a half while keeping the solution scalable. So that's an interesting way to thing to try to do. And the last obvious direction for future work is to try to actually implement this solution. Try to figure out the concrete crypto system that you want to use, the concrete non-interactive zero-knowledge protocols that you want to employ for that purpose, and see if you can get a reasonably practical implementation. And with that, I'm done. Thank you.
Thank you. Okay. Do we have any? Oh, yes. Suddenly, anonymous person. Shouldn't be anonymous. You're not meant to be anonymous. That's what the ICR ones last week. You weren't allowed to be anonymous, so you shouldn't be anonymous. But the anonymous person wants to ask: is the anonymous committee kept secret also after the end of the protocol?
Well, they can't be, right? They have to use the channels to send messages. And once they use the channels to send messages, the adversary learn who they are. If you had anonymous channels from the other direction where you can anonymously post a message, then plausibly you could. Mm-hmm. But that kind of thing, you know, there's no crypto implementation that you can come up with that will give you channels that are anonymous when you post message to. You just have to either you assume that some mechanism like that exists and use Tor or what have you, or you don't. And in our case, we don't assume that.
Does this cause a problem for your application? Because if once you've started using the channel, you know you've revealed yourself, then you can be corrupted, and because you're looking at a proactive model, then you've got a window where the adversary can start hacking people.
Yeah, exactly. Very, very good. So what you do need your PKI implementation to be proactive in the sense that every party broadcasts a new public key once a month or something like that. And you do need to assume that the adversary cannot corrupt people before they broadcast this. And every time that I actually use the protocol, every time that I broadcast a new message in the protocol, I also choose a new long-term key and discard the old one and broadcast the new one.
Cool. Right, do we have any other questions? Just let me look on Zillit. No, we don't. Okay, let's thank Shai and everybody else in this session again. Big round of applause. You can all put your virtual clapping by putting